Okay, let's
Wait,
see.
can I also
here.
record it? Oh. Okay.
Okay, so I'm gonna go ahead and share my screen. Can everyone see it? Awesome. Okay, so welcome to lecture 5. This is ops. We're going to be going over different types of signals and also your project for the rest of the quarter, or the second project of the quarter, I guess. Previously on ops, we discussed microcontrollers and also voltage dividers. Does anyone want to answer what is a microcontroller, or does anyone remember what a microcontroller is? You can also give examples of it as well.
Anyone, come on, you guys got this.
I think I could programmable.
I think your audio cut off there, but I think you said something along the lines of a programmable chip, right?
Yeah.
Yeah, and that's also what Miriam said in the group or the chat. So that is right. So you guys worked with the Arduino Nano. If you were doing it physically, you were also working with the Arduino Uno if you were doing it on Tinkercad. And those are both microcontrollers that you can basically control with your computer to do specific things. And we're going to be delving into the different types of signals that you can produce with a microcontroller in this lecture. The next thing that we discussed were voltage dividers. Now, can anyone explain what a voltage divider is? It doesn't have to be exactly right, and you don't have to just I guess maybe what it's used for. Okay, we have something in the chat. It divides a voltage into two. That's right, Ivan. What's really nice is this is a very common circuit that you find in more complex circuits, but it's a really nice way to get a very stable voltage. So you guys saw the application of a voltage divider in your auto flashlight project when you guys were reading the voltage from the photoresistor. Awesome. So if you guys have any questions, feel free to raise your hand. Otherwise, oops, I guess there was a question, but for some reason, you guys can go ahead and do this question on your own and the answer is right there for you, but it's just a really simple application of the voltage divider equation there. And we can go ahead and move on. Again, this time on ops, we're going to be talking about digital, analog, and PWM signals, also some pull up, pull down, and button debouncing, and then our project 4.
Yeah. So the first signal that we have for you guys is an analog signal. So analog signals are continuous signals, which means that they don't have like set values. Rather, they go from basically they can be like anything. So they can be like 0, 1, 2, 3, 4, 5, and like anything in between. So there's like a lot of different values, and we see that with our graph there, how it can go like up and down, like anywhere there. And so this is sort of the signal that the real world works in, right? Not everything is in ones and zeros. And so the analog signal is what's most obvious to us. And examples of that are like sound or time, how they can have a continuous range of values.
Yeah. Oops, sorry, sorry, hold on. Yeah, so another little blurb here, it says you can almost think of an analog signal as your life. It's like you grew up and you continued and you went through schooling, you're in college now, and your life doesn't stop. There aren't ons and offs. You are just continually living. So that's how you can think of an analog signal. The next type of signal that we have is the digital signal. And digital signals are kind of what computers are or not kind of, it's what computers are essentially made up of. It's not found in real life, but you can use digital signals to make technology run. Digital signals are non-continuous signals, and they have definitive highs and lows. So you can either only have an on or off value with a digital signal. And this can turn a computer on or off, which is really nice. And again, it's what technology is basically, or a lot of technological components are made up of, are digital signals. So what is the big difference between a digital and an analog signal? We can think of, again, an analog signal as a real world signal, and then a digital one as a computer signal. So I have a question for anyone in the audience. What's the issue with having these two different types of signals when we're working with them? Like, what is the problem with that? You can also type it in the chat. Yeah, exactly. So Miriam and Theo also kind of touched base on that. You have to be able to convert between digital and analog signals somehow. And it's not completely obvious the way in which we do that, because how do you make something that's continuous into something that is discrete, and vice versa? So another question is, yeah, again, how do you turn something continuous into ons and offs? And that, Preston, if you want to take.
Yes, and that is where PWM comes in for. So PWM stands for pulse width modulation. And what it allows us to do is we want to represent an analog signal, but we're working with a computer. So we don't have a signal that goes up and down. We just have 0 and 5 volts that we can output. And so how can we tell the computer that we want a range of values with just those two values? The idea is that you give them a specific duty cycle, which is basically you give it like the high a certain amount period of time and then a low a certain period of time. And then the length of time that that it is high will then correspond to the different analog values that we can have. And so that's how we use, like, we have our analog write thing with our pin, and then this will allow us to have values from 0 to 255 rather than just our digital one, which is super helpful. It is important to note, though, that when you are adjusting the duty cycle, you're creating different voltages and you're not changing the frequency. So they all have the same frequency, and that will come in later. We'll talk about that later. But yeah, so on the Arduino, the Arduino Nano, if you are looking for PWM pins, they're typically denoted with the tilde. And on the Arduino Nano, they are the pins D3, D5, D6, D9, D10, and D11.
Awesome. So now that we've kind of gone over the 3 different types of signals that we can work with a microcontroller, we're going to be talking about a couple of components. The first one is the pull-up, pull-down resistor. It's essentially when pins are connected to nothing, they will read noise values. And noise is something that we don't want in a signal because it can add extra values and will throw off all of our readings. So using a pull-up, pull-down resistor is used to set default values. The pull-up sets the default to high, and then the pull-down sets the default to low. And so we have 2 setups here in which you can use a pull-up, pull-down resistor to, again, reduce the amount of noise that you see when you're building any sort of circuit.
Yeah, so these are specifically helpful for us for our push button circuits, where basically what I mean by the default value is basically when you're checking for whether or not the button is pressed. If you use a pull-up resistor, then it will be, if the button is not pressed, then it will be high. And then when you do press it, will go to low, and then vice versa for the pull down. And we see that pretty clearly in the diagrams. You can see for the pull-up resistor, the 5 volts is directly connected to the microcontroller. And then when you press the switch, then it gets connected to ground. So then it would be ground, versus the opposite for the pull down resistor is that the ground is connected to the microcontroller. And when you press the switch, only then does the 5 volts become connected. Yeah.
Are there any questions about the use of these resistors? Okay, cool.
Yeah, so just as an example, it might be a common mistake to make which is forgetting to put a connection to, forgetting to put the pull up or pull down resistors. So when you're making your buttons, so you want to make sure that, like we have on the right, you have, if you want to do a pull up resistor, you have the resistor connected to ground at the end, that you don't just have this, the switch button.
All right, the next thing that we have is button debouncing. Oops, sorry, hold on. So one of the issues with a push button is that they don't change the state instantly. So what happens is you have this bouncing, and on the graph here, you can see that there's a lot of this noise that you see before you even or once you press the button. So it's not exactly on and off. And that becomes an issue again, because noise adds some delay to our actual system. And then we're going to have a lot of problems later on. So because you have this oscillation between on and off before the push button is deemed as on, your system is essentially going to be reading multiple unintended button presses. And so that's the reason why we need to use debouncing in order to reduce this oscillation. And so there are two different types of debouncing here. There's hardware debouncing and software debouncing. Are there any questions about why we are seeing this oscillation when we press a push button, or why we're seeing this issue? Okay, awesome.
Okay, so the first way which you can stop bouncing of the buttons is by using hardware. And in this case, we want to use a capacitor. And why do we want to use a capacitor? It's because capacitors have a timing application. So we use the fact that capacitors take a certain time to charge, and that it takes a long time to charge them, because we can use that then to make it so that it only sends the signal in the amount of time that it's charging. And basically we get it so that it's just completely high for that whole period, rather than during the time it would have been going up or down, basically. So yeah, if you look on the diagram, we basically add a capacitor, sort of, it looks almost like it's in parallel with the switch, if the switch is connected. And that also connects to ground. And then when the switch, in long time, the capacitor is gonna be charged if like the button is just not being pressed. And then as soon as you press the button, then the capacitor will discharge really quickly. And then once you release the switch, it has to charge slowly back up. But this will basically help debounce the button on the hardware side.
Perfect. And then we also have the software side of debouncing. The idea is to essentially wait to read in the value until after you've pressed the button. So we have some pseudocode here, and we'll kind of go through it. You can essentially, what you're going to do is, when you read in the switch state, and then if the state has been changed, then you start a debouncing counter. Basically, you start a counter to pause, and once that counter has been, gone through, then you can read in the value. So you're essentially just creating a pause before you read in the value of the switch itself. That way you're basically ignoring all of the bouncing that you've seen beforehand in the graph. I can also explain that a little bit better. I know that was a little bit confusing, so let me know if you want me to explain it in a different way. Okay. Preston, did you want to add anything to
No,
software debouncing?
That's about it. Yeah, you basically just have a little timer to basically eliminate that with code. Is I think it's easier than the hardware one, but yeah, you just set a little timer to check to make sure that you don't do multiple presses in a row.
Awesome.
Yeah.
All right.
Yeah.
Does anyone have any questions about anything? Feel free to raise your hand.
Don't you like this GIF that I found, guys? I like the little eyeballs moving. It's great. Okay.
All right.
So RGB LED. So we've worked with LEDs before in our circuits, but generally we just have an LED with one color, which would just have just two pins, obviously just like the input and output from the LED. But an RGB LED basically puts a green LED, a blue LED, and a red LED all into one single LED. And so each R, G, and B value, each of those pins, if you look at the little picture on the left hand, there's 3 different pins, which each correspond to the different LED, and then they all share a common cathode. Not always, sometimes they share a common anode, which means that you would want to all put in the same thing. But for us, they share a common cathode, which means they share the ground basically. But yeah, so you want to give both the R, G, and B pins their own PWM signal. So this now is going to be analog, which is going to allow you to get this whole range of color that you see on the right by just varying the different values that you give the R, G, and B. Can give you all of those colors that you see there, which is really cool, and will allow us to have an RGB LED. So that's really cool.
All right. Also, and the reason why we're talking about all of this is because it's relevant to your iPodduino project, which we'll be discussing in a little bit, but don't think that we're just throwing a bunch of random components at you. Another important thing to keep in mind is software libraries. Essentially, programmers and coders are really lazy and they like to reuse code, which is why we use libraries in general. So essentially what you can do is using software libraries allows you to use previously written code and use it into your own program. In C++, we can use codes, and in order to do that, you just do #include and then double parentheses, whatever the library name is, and it always ends in this .h. Yeah. So that's how you, oh yeah.
Yeah, and you want to make sure, like, for the specific library, you also want to make sure you have it in like the folder with your code too. But yeah, so once you have the library and you put it with your code, then you just use that include statement. And yeah, it's awesome. Then you can use all the code from that library. Okay, and now introducing our 4th project, the iPodduino, created by past IEEE President Brian Wong. This is our most fun project yet, and it sort of, we get to use a lot of different things and finally make something which is actually fun and cool. Not that the other projects weren't, but this is just especially so.
So the premise of the iPodduino project is you're going to be creating a system that generates 3 different songs depending on the button that you press, and you'll also be creating your own display. Now, the first part of this is creating your own sound. Now, sound, some of the basic components of it, it's important to understand that the higher the frequency, obviously the higher the pitch, and vice versa. The lower the frequency, the lower the pitch. Now, in order to create this sound, we're going to be using the analog write function.
We're not going to be using the analog write because analog write function varies the duty cycle, but not the frequency, which is what we were talking about earlier. Is like when we typically give a PWM signal, we vary the duty cycle, but for creating sound, we want to vary the frequency. So instead we use a new function, and that function is called tone, which will allow us to change the frequency.
Yeah, my bad. We'll be using analog write for another aspect of the project.
Yeah.
But using tone, again, changes the frequency of the PWM wave. And this generates obviously higher frequency or lower frequency, which can change the sound itself.
Yeah, so like we just said, now we have tone, which is a new function that we're using, which you input a pin and the frequency that you want to give it, and it will generate a 50% duty cycle PWM square wave at the specified frequency. So this allows you to change the frequency of the PWM wave, which you are outputting, and that will allow you to get different musical notes. And so we have a library that we have for you guys to get. We'll talk about it on the next slide, but we have a library, we have the link there, which will give you the different translations of what the different notes are and pitches, so that you can display, so that you can send out a specific note with the tone function. And we also have no tone, which will then just stop generating the PWM wave that you were generating. And you can use a tone to no tone ratio for articulation, and about 1/3 to 1/4 sounds nice for normal notes typically. And we have some little code in the top right, which is sort of an example of what we want to do with this, which is creating like a play function where we're going to use tone and then delay and then no tone and then another delay basically, which will help us in this project for creating music.
All right, so talking about the library pitches itself, it defines all note as a pitch. So you have note C4 is equal to 262 hertz. And you can essentially, when you pound include pitches.h, you can just use these notes instead of having to figure out what the frequency of the middle C is or the frequency of the D key. So this is a really easy way of, instead of having to figure out the frequencies that you want, you can just look at some sheet music and then generate your own song from that. So this will make the project a lot easier for you guys in order to create your own songs. To use it, just download it and put it into the same folder as your program. That's really important. Otherwise, your code won't be able to run because it won't be able to identify what library you're talking about. And then also always include the pound include pitches.h at the top, and then you can just use, again, those defined values in your play function, which will also be talked about in your spec. So you don't have to be able to understand exactly what play does just now.
And if you want to look at all the different notes that there are in that library, you can just open the file, the .h file, and it's just a text file, and it has all those defines for what the different notes are that you can use. Yeah. So part one, the most obvious part of the iPodduino project is actually creating the sound. So we want you to write a song minimum of 10 notes using the play function that you're going to write and play it through your speaker. So we have an example song here that you guys have the slides, so you can look at this later, but you can put it in your code as an example. We have Despacito. It's sort of showing the age of this project now that is our example. But it's very beautiful. And also, don't worry if you're not very experienced with songs and like trying to string notes together. Honestly, that's where I was last year. I'm not a very musical person. We also just have some like very basic, easy songs with notes there that we have links to. So you can just do those if you don't want to. But yeah, so you're actually, it says write a song on this, but you're going to be writing 3 different songs. And yeah, basically you just have to write out the song note by note with your play function. It's pretty cool though, because you can, like, when you actually play it through the speaker, I don't know, it's just cool. It's awesome.
All right, part 2 is creating an interface. And this is when you're going to be implementing an ability to choose which song out of the 3 that you've created. So depending on which button is pressed, it'll play a different song. However, you don't have to worry about when buttons are pressed while your song is playing or anything like that, because that can get a little bit more complicated. So they only have to play different songs when the song that you were originally playing has already ended. We've also included some pseudo code for reference, and this is also in the spec. So if you guys have any questions, feel free to check out the spec for that.
Yes. And finally, part 3, the display. We're bringing it, the last part of our lecture, coming together, our RGB LED. So we want to implement an RGB LED display, which will change its color depending on which song is playing. So basically you want to have a different color for each song. And something to note for this one, which is not on the slide, is that for this, you do need a PWM value for each of the RG and B of the inputs to the RGB LED. So for that, you will be using analog write to generate that PWM signal. So for the music, you use tone, and for the RGB LED, you're going to use analog write. But yeah.
All right, and we will be having a competition once the project is done, and you guys are going to be turning in a video of one of your favorite songs, and then everybody else will be voting on the best song. So try to put in, the amount of effort that you want into it. It's a really fun time, and we'll try to bring out some really cool prizes and stuff like that.
Yes,
so.
Winners get prizes, and not just, you will also be getting a lot of lab bucks, but you get lab bucks and prizes, probably. Definitely. It will be awesome.
All right. Does anyone have any questions about the competition itself?
Or about anything in this whole lecture? Any questions?
All right. Well, thank you for coming out to Ops Lecture 5. Oh, did we get something?
Will there be a work session?
Probably. We're going to try and get a work session in soon. In terms of parts pickup, if you are in the area, we're going to do the same thing where you can come in to pick up your parts. However, if you are not in the area, then we are working really hard to get parts shipped to you. It's just taking a little bit longer than we expected. And we might have to do some variations in the project like due date just because of some people not getting their parts in time. So everything will be, the spec will be released fairly shortly, and then you'll get all the information about due dates and stuff like
And
that.
worst case for this project, it can also be done in Tinkercad if everything stays online next week. I think they have to decide next week, but yeah. So worst case, we'll just be doing it in Tinkercad again. So yeah. But yeah.
I had a question for everybody who's picked up parts before. Does Tuesday or Thursday work better for you guys? Or would you guys prefer Monday and Wednesday? I agree. Tinkercad is pretty cool. Tuesdays, Thursdays. Okay, perfect.
both.
Tuesdays and Thursdays work for me. So, all right. Thank you guys so much for coming out again. We look forward to seeing all of your guys' iPodduinos. I want to see your guys' musical talents. I'll stop sharing now. And I guess that's it. Thank you.